Okay, so we're going to be looking at this reaction right here. And then we got some information that's not that important. So for part A, we're going to start by writing the equilibrium constant expression. Okay, so let's start going over that. Okay, so for the equilibrium constant expression, key thing that you guys should notice here is that it's Kp. So we're going to be talking about it in terms of pressures, okay? So instead of writing the brackets for concentration, we'll be doing it with P for pressure, okay? So the equilibrium constant expression is equal to the products. So the pressure of the product. And since the coefficient is 2, it's going to be squared divided by the pressure of N2 and then the pressure of O2. So just a little notation thing that you guys should notice. If it is a gas, we're going to be working with pressure. If we are working with molarity, we're going to be, or aqueous stuff, we're going to be working with concentration. Okay, just a little notation stuff. Okay, any questions about this one? Hopefully not too bad. Okie dokes. Okay, so we're going to move on to part B. So it says that the student injects, excuse me, nitrogen gas and oxygen gas into this vessel, and it raises the temperature to 2000 degrees Celsius. And at this temperature, the initial partial pressures of N2 and O2 are 6.01 atm and 1.61 atm. So I'm just going to jot that down right here. Okay, so the partial pressure of N2 is initially 6.01 atm, and I'll just write an I just so we're clear. And then the pressure of O2 initially is 1.61 atm. So we're just pulling out some information from the problem. And basically the problem is asking us to find the, the Kp. Okay, so if we have the initial pressures and we want to find Kp, what do we need to use in order to solve this problem? Ice table, yes. Smooth. Okay, so I will give you guys about 6 minutes to try that out. Make your ice table, try to figure out the equilibrium concentrations, and then calculate the value of Kp, okay? And then if you want the equation, I'll write it right here. And I'll move stuff around later just to keep it a little organized, but this is your equation. Okay. So take about 6 minutes, make the ice table, calculate equilibrium pressures, and then the Kp, and then we'll go over it together, okay? Okay, so I set up my ice table, and you put the initial concentrations, and you start with no, yes. And then it gives you the equilibrium concentration of NO at 0.122 atm. Okay, so we can figure out what the changes for each of these. Obviously, we're going to be losing a certain amount of N2 and O2, and we go by the mole ratio. And then we're going to be gaining a certain amount, and that's going to be equal to 0.122. Okay, and so if you divide this by 2, that will give you your change right here. And so you will be losing, 0.061 atm for each of them. Okay, I'll leave one of them X, one of them this one, so you guys can tell they're equal to each other. So you'll get 5.949 here, and then you'll get 1.549 atm right here. And that's how you get the equilibrium pressures. Okay, any questions about that part? Not too bad. Yeah, so the big key right here is this box right here is kind of the key that tells you how to do everything. It's going to be the change right there. All right, we're just going to plug it into our Kp formula. So it's going to be 0.122 atm squared divided by 5.949 times 1.549. That will give you a final answer of about 1.62 times 10 to the negative 3. If you want to write it in decimal form, something like that. Okay, either of those is fine. As long as you're close to that, you're good. Okay? Any questions? Alrighty, guys. So let's look at part 2 now. So here it tells us to find the mole fraction of N2 at equilibrium. Okay, now mole fraction basically means we need to find the percent or the fraction of N2, and that's going to be basically equal to the moles of N2 divided by the moles total, right? Now, if you take a look at this, you might be like, what do I do? Because we don't have anything about moles, right? All we got is pressure, we got temperature, and so you might be thinking, oh, we can use PV equals nRT. However, we can't use that because what are we missing? Yeah, volume. We don't have volume. Okay, so we cannot use PV equals nRT, but you guys can think about the properties of ideal gases. And if you think about ideal gases, we assume that the gases themselves don't take up any space, that they don't attract or repel each other. Basically, they have a very similar relationship with each other. Okay, so one property that we do know is that the total pressure is equal to the partial pressures combined together, right? Okay, so with that being said, for an ideal gas, we could make the assumption, I think this was in your reading that all of you guys do every day on time, and we can assume that the total moles in the container will be equal to the sum of the moles of all the gases as well. So that's going to actually allow us to figure out the moles based on this relationship right here. Yeah, so you can basically use these same numbers and just say that they're moles now, okay, because they're going to have that same relationship. Yes.
Demonstrate our thinking like that to show that we know we're like.
As long as you label the numbers as moles, you should be fine. Yeah.
Like,
Yeah, you don't need to prove it. Yeah. All right, so for the mole fraction, okay, so the percent N2 is going to be equal to the moles of N2, which is going to be equal to the pressure. So 5.949 divided by the total. So you're going to add up all three of these guys. I need my calculator.
7.6.
I don't trust you. I'm sure that's right though. All right, 7.62. 7.62, and then you can multiply either by 100% or you can give it as a decimal. So it'll be 78.1%, or you can use the mole fraction, which will be 0.781. Either or is fine, as long as you label it. So here you would have no unit of measurement. Here you got to add a percentage. So 78.1 would be incorrect. 0.781% would be incorrect, but as long as you got the units of measurement. That's close enough. Yeah. Usually plus or minus like 5%, 5 to 10%. Alrighty, you guys good with that one? I know.
This makes sense right now. Let's see.
Good, good. That's the point. I lull you into a false sense of security. Okay, let's move on to part C, and then that's, I think, the end. Yeah, that's gonna be the end right there. Yeah, that's gonna be the end of that FRQ. There's gonna be about, I think, a little bit longer than this one, but not too much longer.
Would this be considered a short or a long?
This would be considered a long FRQ. Short would have like 1 or 2 parts max. All right, so here you're gonna repeat the experiment in B, but this time you're gonna begin the experiment with more pressure for N2 and O2 in the same container. Same temperature, reaches equilibrium. So I just want you guys to write a brief explanation. Do you think the value of Kp will be larger, smaller, or the same as that in the previous one? Okay. The only thing that's changed is you start with more of each reactant. Okay. So take about maybe 2-3 minutes to write that down. and then we'll go over it, and then we'll be done. Okay, so equilibrium or the KP value will eventually be the same. Okay, now let's talk about KP. What is KP? Somebody, yeah, it's a ratio. KP is a ratio of what? Not ration. Ratio. Of the reactants and products. Okay, and more specifically, it's going to be the products divided by the reactants, right? Okay, so what that means is that no matter what happens, no matter what you start the reaction with, if it starts going towards equilibrium, at some point you're going to have the same ratio between the reactants and products, right? So let's go back to the original problem. If you start with a lot more or more N2 and O2, is that going to change KP at all? No. Okay. So in this case, no. Starting with increased pressures of N2 and O2 will not change KP. And the reason why is what we talked about earlier. It's a constant for each reaction at every temperature. It's a ratio between the products and the reactants. Even if you start with more reactants, you'll probably end up with more products, but the ratio will stay the same. Okay. That's it. Yay. So if you wanted to do, yeah, great job, everybody. If you want a TLDR, KP does not depend on initial concentrations. Yeah. Yeah. Yeah, if you didn't want to give this and you just wrote that, that should be fine too.
If it doesn't say briefly explain, can you just say?
I would for yes and no or same stuff, I would always add at least a little blurb about why. Doesn't have to be super in detail, but just something like this. Yeah. Just in case, you know.